Principles of Bioproduct Separation Module 5 Extraction Segment 1 with me, Yusuf from Bioengineering Study Program, School of Life Sciences and Technology, Institut Teknologi Bandung. In this module, we will discuss about chemistry of extraction, batch extraction, stage extraction, differential extraction, fraction extraction with two moving phases, last but not least, exercises. At the end of this module, students will be assigned to do several exercises to determine partition coefficient, determine fraction of extracted components, determine number of stages, determine extraction time and concentration profile. Liquid-liquid extraction is the separation of two or more components from a liquid mixture into two immiscible liquid phases based on their unequal solubility as illustrated in the figure. This method is also known as solvent extraction. Chemistry of extraction. The extraction process is based on the partitioning of a solute between immiscible liquid phase, which can be expressed by equation 1. In many cases, light phases will be an organic solvent and the heavier phase will be water. Often, the values of K will be constant, independent of solid concentration for a given solvent pair. A constant K reflects the fact that most biochemical extractions take place in a dilute solution. Values of K must be found by experiment, but generally depends on the chemical structure. Chemical potential of the solute at equilibrium is constant and equal in each phase as shown in equation 2 and equation 3. Equation 3 can be easily rearranged to yield equation 4. Figure in the left shows solid chemical potential versus chemical concentration. Equilibrium occurs when the values in the feed and solvent are equal. H normally present in excess, hence the chemical potential μH of the solute in the solvent is fixed, as shown in the figure. In principle, as the concentration X gets large, μL will approach the standard μL. In practice, μL may be limited by solubility, as indicated by the dashed line. The intersection of μL and μH gives the concentration of X present in L. We can see that changes in L will change X. If we change L so that its standard energy is raised, we lift the entire curve for μL and thus decrease the equilibrium value of X. In contrast, if we reduce standard μL, we will increase the value of X. But how can we change standard μL? We have two routes. First, changes in the solvent. Second, changes in the solute. Changes in solvent. The most obvious way to change standard μL is to choose a different extraction solvent. The partition coefficient K can be written as shown in equation 5. We can carry out an extraction with two solvents whose solubility parameters are known. We use the experiment to find the solubility parameters of the solute. We can estimate the partition coefficients for new solvents from their values of the solubility parameters. The partition coefficients for several solutes and solvents are as shown in the table. Changes in solute. Via ion pairs, changes in the solute depend on the fact that the most solute can be ionic. If so, it must have a counterion which can be changed without changing the solute itself. Two changes in counterions are useful. First, the counterions can be replaced with those which are more soluble in the extraction solvent. Second, the solute may be weakly acidic or basic, so that changes on pH will alter the degree of its ionization. Changes in solute via pH. Many of the solutes that we want to isolate are weak acids or bases that can be altered by changing pH. A weak acid can partly ionize in water, but it will not ionize significantly in organic solvents. The apparent partition coefficients lump both ionized and unionized forms can be expressed as shown in equation 6. The concentrations of unionized and ionized solutes in water are subject to the equilibrium as shown in equation 7 and equation 8. Equation 6 and equation 8 can be combined to give equation 9. Combining equation 9 and equation 10 leads to equation 11 and equation 12. For solute A and B, the selectivity of a separation can be calculated by equation 13. For the next segment, we will discuss about batch extraction. Until then, I am Yusuf from Institute Teknologi Bandung.